So in this video, we'll be discussing trigonometric ratio. However, before we explore the concept of trigonometric ratio, first let's ask ourselves, what is trigonometry? What is trigonometry? Now, observe closely. This word trigonometry originates from two Greek words, trigonon, which means triangle, okay, and metron, which means to measure. So from here, it is obvious that trigonometry simply deals with what? The measurement of triangle. So whenever you um, see anywhere where the word trigonometry is used, or whichever form, whether it is used as an adjective or it is used directly as a noun, you should know that it definitely deals with measurement of triangle. So trigonometry is a branch of mathematics that deals with what? That deals majorly with relationship between angles and sides of a triangle. Of course, when we say triangles, triangles is a topic on its own. But when we say triangles, it's a shape that has three sides, with these three sides forming three angles with themselves. There are different types of triangles. We can classify triangles based on the type of angles present. We can classify triangles based on the sides that are present. But however, our major topic under trigonometry is the trigonometric ratio. Now, what is the trigonometric ratio? Okay, let me just paste the definition here. So, trigonometric ratio um, is nothing but what? The ratio of the sides of a right angled triangle with respect to its angles. So, they are fundamentals to trigonometry and relate the angles of a triangle to the lengths of its sides. Now, a right angled triangle. A right angled triangle is a type of triangle that has one of its angle equal to um, 90 degree. So let me sketch a right angle. Let me bring in a right angle triangle. Okay, a right angle triangle. This is a right angle triangle, and commonly you will always see um, something like this always indicated at the corner here to show that this angle is what is 90 degree. Now, conventionally, we label the vertices of a triangle with capital letters. For example, I could say, this is A, this is B, and this is C, where that is this triangle has three sides: side AB, side AC, and side BC, or you say side CB. Okay. Now, this let's assume a particular angle is given. Let's say this angle is given to be theta. Okay. Now, this angle theta is directly facing side AC. So in that context, we label this side AC as our opposite, right? And the other side, other than the one facing the 90 degree is labeled as our hypotenuse, which is always the longest side of a right angle triangle. And the last side is labeled as the adjacent. Obviously, if we are considering another angle, let's say we are considering the other opposite angle here, let's say this is alpha, then automatically we have a change of configuration. Our opposite now is going to be our CB, our adjacent is going to be our AC, while the hypotenuse still remain um, AB. But for this case, let's deal with theta facing AC. All right. Now, conventionally also, it is also a common practice for us to label the sides based on the angle they are facing. What do I mean? This um 90-degree is facing the hypotenuse. So by convention, we could say let us label that hypotenuse as C, small letter C. The adjacent in this case is facing angle A. So by convention, we could label it as small letter A. And the opposite, AC, is facing angle B. So we could label it as small b. Okay? So that we have our triangle to in this form. Okay? We have our triangle like this, such that this is C, this is C, this is A, and this is B, and we have our angle here labeled as theta. With this, okay, let's indicate our 90-degree. With this, now, how do we now get all the trigonometric ratio for this triangle? As defined, we say trigonometric ratios are the ratios of sides of a right angle triangle. Now, there are various possibilities of combination of ratios, okay, that we can obtain from this triangle. Now, the common trigonometric ratio that we are familiar with is the ratio of opposite to adjacent. Okay, we also have the ratio of opposite to hypotenuse and the ratio of adjacent to hypotenuse. Right? Now, the ratio of opposite to adjacent is commonly known as the tangent of the given angle. Okay, of the angle indicated here in this context, theta. While the ratio of opposite to hypotenuse is the sine of the angle, and the tangent, the last one, adjacent to hypotenuse, is the cosine of the angle given. Okay, there's a common mnemonic that we use for remembering the common trigonometry ratio, which is so katoa, which indicates that sine is the ratio of opposite to hypotenuse, cos is the ratio of adjacent to hypotenuse, and tan is the ratio of opposite to adjacent. Now, before we delve too deep into the trigonometric ratios, now there is another very important concept um, about right angle triangle. That is the Pythagoras theorem, popularly known as the Pythagoras rule. Call it the Pythagoras rule, or we call it the Pythagoras theorem. Okay, Pythagoras theorem shows the relationship between the sides of a right angle triangle. Okay, and it is nothing but it's Pythagoras theorem states that the square of the hypotenuse of a right angle triangle is equal to the sum of the squares of the remaining two sides. So now, take for example this particular triangle that we have, triangle ABC, where the hypotenuse is C and the remaining two sides are A and B. Here, our hypotenuse C squared is going to be equals to what? A squared plus what? Plus B squared. This is known as what? The Pythagoras theorem. In the case where C is our hypotenuse and A and B are the remaining two sides of the right angle triangle. Now, there are other possible cases. Now, let's go back to our trigonometric ratio. There are other possible cases of the trigonometric ratio. Like, what if we consider adjacent over opposite? Or what would we consider hypotenuse over opposite? Or what would we consider hypotenuse over adjacent? These are definitely still ratios. Of course, these ratios also have their own names. Okay? For in the case of if we invert the tangent we get what we call the cotangent. So we have cotangent of theta is nothing but the reverse, that is adjacent over opposite, which is the same as saying the inverse of tan theta. Okay. Also, we could also have the cosecant, as we call it cosec, the cosec theta, and the cosec theta is inverse of sine theta, which is over hypotenuse over opposite, hypotenuse over opposite, which is nothing but the inverse of sine theta. And also we have secant theta, which is popularly shortened as sec theta, which is equals to what? The inverse of cos theta, which is hypotenuse over adjacent. That is inverse of cos theta. So these are the other possible combinations for a right angle triangle that we could have. Now, using these same triangles, we could get what will be the value of tan theta using this triangle. Of course, we have already identified our opposite as being B, our hypotenuse as being C, and our opposite and our adjacent as being A. In this case, it implies that our tan theta is going to be what? Is opposite over adjacent, which is B over A. And our sine theta is what? Is opposite over hypotenuse, which is B all over C, while our cosine theta is what? Is adjacent over hypotenuse, which is A all over C. So let's demarcate this. So this is for tangent. This is for tangent. This is for um, sine, and this is for cosine. So these are the common trigonometric identity that we have. These are the common trigonometric identities that we have. But we said we can also extend this to this. Now, if we try to, if we try to, we can also write in terms of the A and B that we have labeled. So meaning that the tangent is just going to be the reverse of what we have here, which is A over B. And the cosecant, which is cosec theta, is going to be C over B, while sec theta is going to be C over A. Now, we can combine the idea of the Pythagoras theorem and the various trigonometric ratio that we have obtained. We have, from our triangle, let's redraw the triangle again. From our triangle, we have this as our triangle, where this is labeled as C, as B, and as A, and this place as theta. And we have written that C squared is equals to what? A squared plus B squared. Now, let's divide through, let's divide through by C squared. If we divide through by C squared, obviously we are going to have C squared over C squared equals to A squared over C squared plus B squared over C squared. Now we could rewrite this as, of course this one is 1, we could rewrite this as A over C squared, law of indices, plus we could write this one as B over C also all squared. Now remember that we have established that our sine theta is B over C and our cos theta is A over C. So from there, we could substitute directly here and have 1 equals to our A over C is cos theta. So we could have cos theta all squared here and sine theta all squared. This is commonly written as Cos theta all squared is the same thing as, is also written as cos square theta, while sin theta all squared is also written as what? Sin square theta. Meaning we are not squaring theta, we are squaring the value of um, cos theta and the value of sin theta respectively. Okay, so this is one of the identities, one of the trigonometric identities that you must always remember. It's very, very handy when, especially when dealing with what, simplification of trigonometric expression. Also, what if we have divided through by another letter? Instead of dividing through by C, what if we have divided through by another letter? Are we going to get anything? Now let's try that. Let's assume, instead of dividing through by C, let's assume we have divided through by um by a squared. We have divided through by c squared here. Let's divide through by a squared and see what we are going to have. Okay, if we divide through by a squared, then what do we have? We have c squared, we have c squared divided by a squared equals equals a squared divided by a squared plus b squared divided by a squared. Then what does this give us? We can also rewrite this as c over a all squared equals to 1 plus b over a all squared. Also previously established, we have obtained what c over a is. C over a is sec, that's sec theta. So we have c over a, we have sec theta, which you can write, because of the square, you can write as sec square theta equals to 1 plus, on our b over a has also been, our b over a has been obtained as tan theta. So that's 1 plus tan squared theta, tan squared theta. So this is another identity that we obtained by combining what? By combining the Pythagoras rule and the trigonometric ratio. Also, we can, what if we divide through by b squared? Let's see what we get. Let's divide through by b squared. If we divide through by b squared, then we would have had c squared. You could do this. You can pause the video and try this on your own and compare your answers with mine. So c squared divided by b squared equals to a squared divided by b squared plus b squared divided by b squared. Of course, this can also be written as c over b all squared equals to what? A over b all squared plus 1. Okay, rearranging this, you get c over b has also been previously established. Our c over b is cosec, cosec theta. So meaning here we're going to have cosec square theta equals to, and our a over b has also been obtained as cot theta. So what we have here is what? Cot square theta plus 1. So this is another identity that can be obtained by a combination of what? By a combination of the trigonometric ratio and the the Pythagoras rule. Now, so this gives us the three common trigonometric identities that can be obtained from combination of Pythagoras rule and the trigonometric ratio. Now, knowing these identities is not as important as knowing how to use them to solve, to simplify trigonometric expressions. So, check out my other videos where I showed you how to solve simplification problems relating to trigonometric ratio, how to use these identities to solve trigonometric problems.